For our second example of a titration curve, we'll look at the titration of a weak acid by a strong base. In fact, this is example 2 from lecture 3, in which we're titrating 25 milliliters of acetic acid, 0.09508 molar concentration, with 0.1219 molar sodium hydroxide. From that example, we found out that it took 19.5 milliliters of the titrant to reach the equivalence point. That would be where exactly all of the acetic acid was reacted. That was initially in the flask, and that the pH at the equivalence point was greater than 7. As with the previous example of a titration curve, our first example, we could record the pH as the sodium hydroxide titrant is added with a pH meter, and we could add the sodium hydroxide in small increments right up to the equivalence point and beyond the equivalence point. If we did that, the titration curve would look like this. Remember, the equivalence point is when we've added 19.5 milliliters of sodium hydroxide, and here the pH is greater than 7. It's actually 8.74. We've worked that out previously. We need to note that this titration, this current one we're looking at, the weak acid titrated by a strong base, is directly comparable to the previous titration curve, the strong acid titrated by the strong base, because each titration starts with the same number of acid molecules in the flask, 2.377 times 10 to the minus 3 moles in 25 milliliters, and uses the same concentration of strong base titrant, 0.1219 molar. In addition, you'll notice, or you will soon notice if you look back at the previous example, that the increments of sodium hydroxide added are exactly the same as in the previous titration of the strong acid by the strong base. So these two titrations are definitely directly comparable. As before, we'll look at and try to calculate the pH in 4 key areas of the titration curve. The initial pH before we add any titrant, the pH in the region between the initial pH and the equivalence point, the pH at the equivalence point, and the pH in the region beyond the equivalence point where excess titrant has been added. These 4 points, where there's 0, 13, 19.5, and 24 milliliters of sodium hydroxide added, again, are the same points we looked at in the strong acid titration. Now, as mentioned previously, it's usually a good idea to calculate the number of moles of acid, in this case acetic acid, present initially in the flask. And yes, we already know the answer to this, but in practicing good form, we'll go through the calculation. The number of moles of acetic acid present initially would be the volume times its concentration, 2.377 times 10 to the minus 3 moles of acetic acid. Now, since this is a weak acid, the number of moles of hydronium ion in the flask is certainly not 2.377 times 10 to the minus 3 moles. Because remember, acetic acid's a weak acid. Most of it stays in this form, so we will produce some hydronium ions, but not that many. So we need an ice table to calculate the pH. So essentially what we're doing is calculating the pH of a 0.09508 molar solution of the weak acid acetic acid. In other words, this many moles in 25 milliliters total volume. We set up the ice table. We use the usual methods with the proper Ka value. We get a pH of 2.88. Now recall that the initial pH was much lower when we titrated the strong acid with the strong base, because the strong acid, of course, would have the lower pH, or another way to think about it would be the initial pH in the flask should be higher for the weak acid, acetic acid, than for the strong acid. So let's calculate the pH after addition of 13 milliliters of sodium hydroxide. This is in the region between the initial and the equivalence point. Well, at 13 milliliters, the number of moles of hydroxide added would be the volume times the concentration, or 0.0015847 moles of hydroxide. Recall that the hydroxide should react with acetic acid to produce acetate ions. And we can keep track of this. So before addition of hydroxide, we have this many moles of acetic acid, essentially very few moles of acetate. When we add hydroxide, we react with the acetic acid and produce that same number of moles of acetate as moles of hydroxide added. And so after reaction with hydroxide, we have this many moles of acetic acid left, and we've produced 0.0015847 moles of acetate. Well, this is a buffer. We have significant concentrations of the acid form and the base form of a weak acid. So we'll bring in the Henderson-Hasselbalch equation. We'll use the pKa of acetic acid and the number of moles of acetate divided by the number of moles of acetic acid. We take the log of that ratio. We get 0.30. So the pH would be 5.04 at this point in the titration. Well, how about at the equivalence point? Well, recall at the equivalence point, again, the pH would have to be greater than 7 because we've produced acetate, which undergoes hydrolysis in water to produce a little hydroxide. Sodium ion's neutral, and of course water's present. This was worked out previously, and we calculated the pH to be 8.74. We could actually get this result right from the titration curve without even doing a calculation. If you estimate the equivalence point as being halfway in this steeper rise here, and again, we remind you that if we had enough data points in this area, we could get a more exact position for the equivalence point by looking at the first and second derivatives of the data. For now, we're doing it by eye. The equivalence point volume would be the volume of NaOH at that point in the titration, at the equivalence point. And the equivalence point pH, of course, would be the pH at the equivalence point. Clearly, the pH at the equivalence point is greater than 7. Well, how about in the region beyond the equivalence point? In other words, even when we reach the equivalence point, we go past it, we keep adding increments of sodium hydroxide. Well, as with the titration of the strong acid by the strong base, after the equivalence point, we've totally destroyed the acid that was there, and so everything is controlled simply by the excess sodium hydroxide that's being added. And this is true despite the presence of the acetate ion in solution. So the total number of moles of sodium hydroxide added when we've added 24 milliliters would be 0.0029256 moles. The number of moles of excess hydroxide would be how many we've added in total, minus the number needed to reach the equivalence point, and that would give us the number of moles of excess hydroxide. The concentration of hydroxide would be that number of moles divided by the total volume at that point in the flask, which is 25 that we started with plus the 24, so 49. The pOH would be 1.95, leaving us a pH of 12.05, which, by the way, is identical to the pH we got in the strong acid, strong base titration, because remember, everything here is simply being controlled by the excess sodium hydroxide, and in the two titrations we're comparing, we've added exactly the same number of milliliters of excess sodium hydroxide, and the volumes are the same. Well, let's look at if we wanted to add an indicator, what indicators would be appropriate. And again, before I mentioned for this titration, when we look for an indicator, of course, we want the indicator to change color at the equivalence point. But when you see the titration curve, we can see why in a little better way, why these indicators would work. We noted before that we want to choose indicators that will give us endpoints as close to the equivalence point as possible in order to minimize titration error. And again, remember the titration error would be the titrant volume at the endpoint where we can see a change minus the titrant volume at the equivalence point. That would be the titration error. Here the advantage of plotting a titration curve is that we can get a good idea of what the equivalence point is without using an indicator. But again, if we wanted to look at what indicator to choose and we overlaid a couple of choices on the titration curve, we can see that thymol blue would work. Phenolphthalein works really well here because now the equivalence point is right in the middle of that color change, and remember phenolphthalein changes from colorless to pink, so it's a lot easier to pick up visually than yellow to blue. So now we have an opportunity to directly compare the titration curves for the strong acid titrated by a strong base versus the weak acid titrated by a strong base. Now these two titrations are identical, except that one involves a strong acid, perchloric acid, and the other a weak acid, acetic acid. Now they're identical in the sense that each flask starts with 2.377 times 10 to the minus 3 moles of acid in 25 milliliter total volume. The titrant for both is 0.1219 molar sodium hydroxide, and it's added in identical increments. So what are some similarities between these two titration curves? Well, both titrations required the same volume of titrant to reach the equivalence point, 19.5. Both titrations show a pH of 12.05 when 4.5 milliliters of sodium hydroxide beyond the equivalence point is added, because remember, irregardless of what's going on, what's in the flask, I should say, when you go beyond the equivalence point, the pH is just totally controlled by the excess number of moles of sodium hydroxide. So what are some differences between the two titration curves? One of them is that the initial pH before we add any titrant, and the rest of the pH values before the equivalence point are all higher for the weak acid. Makes perfect sense. The weak acid has this interesting initial rise in pH right here, quick rise, but it levels off when we get into what we call the buffer region. The pH values at the equivalence points are different, so the equivalence point volumes are the same, but the equivalence point pHs certainly are not. The other major difference between these two, and the difference that's usually cited as the most noticeable, is that for a strong acid, strong base titration, the rise in pH near the equivalence point is much steeper than with the titration of a weak acid by a strong base. In fact, the weaker the acid, in other words, the smaller the Ka value, and or the more dilute the weak acid, the more and more this rise in pH starts shrinking until it's harder and harder to see, actually. Now, there's one additional piece of information that's important that we can get from the titration curve of the weak acid by the strong base, and that is we can measure the Ka of the weak acid from the titration curve. Let's see how we can do that. The pKa of the weak acid is equal to the pH value at the half equivalence point on the titration curve. The equivalence point volume is 19.5. If you divide that by 2, you get the half equivalence point. That would be at 9.75 milliliters. Now, from the titration curve, we can read a pH of 4.74 at this half equivalence point. We say the pH at the half equivalence point is equal to the pKa of the weak acid. So the pKa of acetic acid is measured to be 4.74. If we back calculate the Ka from that, we get 1.8 times 10 to the minus 5, a number that should look familiar. In this case, it's exactly equal to the accepted value, meaning the one we've used in previous lectures. Now, why does this work? At the half equivalence point, you've half titrated the acetic acid. And at that point, the number of moles of acid left exactly equals the number of moles of acetate that you've produced. So the second term of the Henderson-Hasselbalch goes to 0. Let's demonstrate. At the half equivalence point, we've added 0.0011885 moles of hydroxide. That would be the half equivalence point volume times the concentration. If we track how much acetic acid is left, we say we started with this many moles of acetic acid. We destroyed this many moles of acetic acid and produced this many moles of acetate at the half equivalence point when we added this many moles of hydroxide. And so after reaction, we have the exact same number of moles of weak acid left as moles of acetate that we produced. So if you write out the Henderson-Hasselbalch equation at this point in the titration, the pH, which is 4.74, equals the pKa plus, of course, the log of the number of moles of base form divided by the number of moles of acid form. In other words, we have the log of 1, and the log of 1 is 0. So we find out that the pH, which is 4.74, is equal to the pKa, and that is of acetic acid. So titration curves of weak acids being titrated by strong bases can be used not only to find the concentration of the weak acid in the flask, but we can also use the titration curve to measure the Ka of the weak acid.